Mathematics is in one way an expression of the nature around us, and it attempts to decipher the nature of that pattern. And there is perhaps no mathematical theory that lies closer to nature than the Fibonacci numbers. From the number of petals in a flower to the spiral galaxy that we see, the trace of Fibonacci sequence is very evident in nature. The first recorded appearance of the Fibonacci sequence is in the works of Indian mathematician Pingala around 200 BC, and later on in the works of Virahanka. Outside India, the work appeared in the book Liberace 1202 by Fibonacci. This is how the world came in contact with the sequence on a large scale. Fibonacci is said to have come up with the idea when he was observing the mating pattern of rabbits in the field, and was intrigued by the question as of how many rabbits will there be in the field at the end of a year if you start with just one male and one female rabbit. A Fibonacci number is defined to be the sum of the previous two Fibonacci numbers, as given by the equation Fn equals Fn minus 1 plus Fn minus 2, where F1 and F2 are designated to be equal to 1, and therefore by definition F0 equals 0. As a result of this definition, the Fibonacci numbers increase exponentially. Fibonacci numbers are seen in many natural settings, such as the leaf arrangement in plants or the number of leaves on a sunflower. The numbers also feature greatly in mathematics, although their uses are not often groundbreaking, or exceedingly useful for that matter. They are incredibly varied in their application. First and foremost, the Fibonacci numbers can be used to approximate the famous golden ratio, as a Fibonacci number divided by the Fibonacci number immediately preceding it draws ever closest to the famous 1.6180339. This is perhaps the most known use of the Fibonacci numbers. The numbers have many other more miscellaneous uses. For example, in a coin tossing event, the probability of not landing two of the same outcome in a row over n amounts of tosses is equal to Fn plus 2 over 2 to the n. Fibonacci numbers can also give you the number of ways a set, including the empty set of the form 1, 2, and on until n, can be arranged without picking two consecutive numbers, which is given by Fn plus 2. The Fibonacci number Fn plus 1 also gives a number of ways 2x1 dominoes can cover a 2x n checkerboard. Interestingly enough, Fibonacci numbers can also be used by investors to predict changes in the stock market through the Fibonacci-based investment system of the Elliott wave theory. In perhaps the simplest and yet most confusing application, the sequence can be used to predict the number of petals in a flower. The sequence is also used in computational runtime analysis of Euclid's algorithm to determine the greatest common divisor of two integers. The Brock-Merman economic growth model is strongly influenced by the ideas of the Fibonacci sequence. Here it is shown how a generalized Fibonacci sequence enters the control function of finite horizon dynamic optimization problems with one state and one control variable. The Zeckendorf's theorem is another area of mathematics that is influenced by the sequence. The theorem states that every positive integer can be written in a unique way as the sum of one or more distinct Fibonacci numbers. In conclusion, the Fibonacci numbers are perhaps one of mathematics' most underappreciated areas, though they lack any serious practical applications in the real world.